Hello?
Hey.
Hey, what's up? How's your day coming along?
Pretty nice. How about yours?
Doing great. Thanks so much for asking. So we're going to be doing the same thing we did yesterday, right? We're just going to continue that page.
Yep.
All right. So if I remember correctly, we left off with this one. We had and I'm just going to use the pen tool to draw the little subscript. So what we're trying to do is we're trying to identify the reaction. And then when we can do that, it'll help us predict what the products could be. So what we have here is we have iron 3 oxide hydroxide. That's what this molecule is called. It's in solid form. What is it called when we just have one single thing, one single reactant? What kind of a reaction does that have to be?
Single reactant.
Well, it is a single reactant, but what kind of a chemical reaction is it when it's just one single reactant and not multiple things? Like, for example, we know that there are certain clues that kind of tip us off about what kind of reaction it is. Well, I didn't need to do that. I never will learn how to use this platform properly. So, for example, if we have this, we know this is going to be a combustion reaction. So whenever we have something appearing just completely by itself like this is a decomposition. We're breaking one thing up into multiple things. So we're breaking it up into two things. We're going to have an iron. And then iron is one of those diatomic atoms. You can't have it appear just by itself. You have to have two of those, if I remember correctly. And we would have an O3. And then we would have a water molecule left over. And I don't think we even really need to balance things. I think they just want us to predict the products and then name the reaction type. So these would be the products. We have iron 3 oxide and we have water. And the type of reaction this is would be decomposition.
Reaction.
Mm-hmm. And as always, let me know when you're ready to continue.
Oh, yeah, I'm ready.
All right. Up next, we have sodium reacting with water to form something else. So we want to think about what kind of reaction this one could possibly be. So one clue is that we have one thing, and then we have a compound made up of two different types of elements. So what do you think that might be whenever we have a kind of a setup like this one? There's going to be some switching.
So there's no product?
These two there's going to be two products. There are two reactants, and then there's going to be two products that result from this reaction. So what is it called when we have things switching around?
It would be called...
Do you think it'll be a single replacement or a double replacement?
I think it's going to be a double replacement.
Well, this one is just going to be a single. Double replacement occurs when we have two things in the first compound and then two things in the second compound switching. But when it's just a single and then a double, this would be a single replacement, because either the sodium is going to switch places with the hydrogen or it's going to switch places with the oxygen. It's just going to be one single replacement going on here. So let's talk about what this could possibly turn into. So typically what happens in a reaction like this is the hydrogen is left on its own. So typically we would have this H2 switch with the sodium. So if in that case, we would have something that looks like this. We would have sodium hydroxide, and then this H2 would be left on its own. So we can see that the things that switch places would be the H2 and the sodium. These are the things that switch places in the single reaction, the single replacement reaction.
Ah. Yep, I got it.
All right. Next up, we have solid lead reacting with calcium chloride, which is an aqueous form, to form something else. So it kind of looks similar to what we had last time. We have the first reactant has one element. The second reactant has two different elements. It's a compound with two elements. So that's kind of a dead giveaway that this is going to be another single replacement. So this lead is going to switch places either with the calcium or with the chloride. So typically, when we have a metal appearing by itself in a reaction like this one, it switches place with not the gas part, not the diatomic part. So typically what happens is it would switch places with this calcium. So this would be another single replacement reaction. And the products we predict from this would be calcium in its purest form by itself, along with one molecule of lead chloride, which would be this right here. Next up, we have a fairly complicated looking one. We have chromium C2H3O2 with a little subscript 3 out front. So inside the parentheses, we have C2, we have H3, and O2. So here, I want to just write the rest of it. So then we have this reacting with something else. This is reacting with nickel, and then we have Cl, chlorine, and then oxygen, and then a little subscript 2 out front, and then O3 on the inside. So let's see if we can identify what these things are real quick to help us understand what kind of a reaction it could be. So Cr is chromium. Chromium is a metal. And then the thing in parentheses is acetate. The little 3 out front means this is going to be chromium 3 acetate. And then we want to do the same thing for our other reactant. So Ni, we know, is nickel. It's another metal. And then inside the parentheses, this time we have chlorate. So this is going to be nickel 2 chlorate because we have a little subscript 2 outside the parentheses. We have nickel 2 chlorate. So before we can predict the reaction, or predict the products, we want to determine what kind of a reaction this is. So in general, whenever we have a metal and an acetate, and then another metal, and then something else that doesn't appear in the first reactant. So for example, we have a chloride appearing in the second, but not in the first, but we have a metal appearing in both of them. This is always going to be a double replacement whenever we have a situation like this one. So the metals are going to switch places, but everything else is going to remain the same. So this is going to be a double replacement. And then our products are going to be this. Let me write them out real quick. It would let me. It might not let me do that. Sometimes my computer just doesn't want to work for some reason. Don't know why, but that's the case sometimes. So
What computer do you have?
Sorry?
Never mind.
Are you sure?
Yep.
All right. So we're going to switch the metals around. So instead of chromium 3 acetate, we're going to have a nickel 3 acetate. And instead of having nickel 2 chlorate, we're going to switch the metals. We're going to have a chromium 2 chlorate. Sometimes I have to threaten to use another computer to make this one want to work again. I think it gets jealous.
Yeah, probably.
It's the only logical explanation as far as I can see.
Yeah, that's the obvious explanation after all.
Indeed. Next up, we have sodium hydroxide in an aqueous form reacting with hydrochloric acid. And what do they form? They form a salt and a water. So what kind of a reaction do you think this one might be?
It will be Perhaps double replacement?
How do we know that for sure?
Well, it looks like one.
Let's label everything. Sodium chloride is just a fancy name for table salt. And then we have so you suggest this is double replacement. And you're right. It is absolutely a double replacement. What tipped you off about it? What made you think double replacement right away?
Well, both sides, they generally share the same amounts of numbers. No, well, letters. It's hard to describe.
So we have an Na appearing with something, and then an A appearing with something else. So that might have been what tipped you off. You might have seen, hey, there's kind of this relationship going on with the sodium hydroxide and the sodium chloride. And then it looks like it kind of broke apart and switched places with this hydrochloric acid. They kind of just did the old switcheroo and went a different direction. So yeah, this is absolutely a double replacement. Have you ever bitten into what you thought was a chocolate chip cookie, but it ended up being oatmeal raisin?
Opium raisin? No, never.
You're lucky. That happened to me today, and I'm still feeling the sting of betrayal.
Betrayal.
Indeed, betrayal. Next up, we have strontium chlorate. And it's just one single compound, strontium, and then the chlorate is going to have, oh, I forgot the oxygen. That would have had very disastrous results if this were a real lab situation.
What would have happened?
I can't even begin to describe.
That terrible?
It would be like, probably like, you know, the science experiment where people make a volcano and they pour, I forget the mixture they pour into it to make it explode. I imagine it would be something like that, but on a much more disastrous scale. So a little number has the potential to have completely disastrous results. Like if you're in a lab and you're trying to decompose this into something, and for some reason you have the wrong subscript, if you made this a 3 instead of a 2, for example, it doesn't seem like it would have that big of a difference, but it actually would. And math is kind of the same way. Math and computer science and engineering, like that's kind of one of the reasons why I decided not to study civil engineering. Because if I make one little mistake with my math, and we have to use calculus, differential equations, analysis, all these different higher level math applications, if I make one little mistake, if I forget one minus sign, boom, the bridge collapses, people die, and it's all my fault. That's kind of why I switched to computer science, because if I make a mistake, the computer tells me, I get a little error message on the screen, and I don't kill anyone. So it's a lot less stressful of a career than chemical and civil. I like stress-free as much as I can. I like to have a stress-free career if possible. Enough of my little anecdotes. So we have strontium chlorate. And then what kind of a reaction is it if we have just one single reactant?
One single reactant, then it would be, it's not single replacement, right?
It is not. We have one thing being broken up into 2 or more things. What do we call that reaction?
We would call that decomp.
Yep, it is decomposition. Perfect. We have strontium chloride, and then we have oxygen. Well, what happened there? Strontium chloride needs to have this little 2, and then the O2. Oxygen is one of those 7 elements that doesn't exist in a single form in nature. Just because it readily bonds with other oxygen molecules That's why an O never appears just by itself in nature. That's why it's always going to be an O2. And there are other elements like that too, like bromine, iodine, chlorine. It's one of 7 that have that property. So we know it's a decomposition reaction. Let's just go ahead and name everything. So we have that. So we know Sr is strontium. And whenever we see, in parentheses, whenever we see something like this, we have chlorine and then a trioxide atom with a little subscript 2. That's always going to be chlorate. So this has to be sodium chlorate. And then let's take a look and see what else we have here. Not going to let me tab all the way out. Okay. So this is going to be strontium again. Sr is still going to be strontium like before. And then Cl2 is chloride. So this is strontium chloride. And then oxygen.
Yep, I got this.
All right. Up next, we have calcium in the solid form reacting with bromine in diatomic form. And this would produce, what do you think this one would be? So we have solid calcium, and I think just for this one, I might put the form in there. This is solid calcium because having the form might help us have a better understanding of what's going on in the reaction. And then this is diatomic bromine gas. So what do you think would happen in a situation like this where we have a solid and a gas coming together? Our choices are decomposition, single replacement, double replacement, synthesis, and combustion.
It would be
what do we call it when 2 things come together to create one single thing? Like, I guess we could kind of consider this one to be the opposite of a decomposition reaction. What do we call this?
well, that would be
So the opposite of decomposition is always going to be a synthesis. So decomposition takes one thing, it breaks it up into 2 or more parts. A synthesis reaction does the opposite. It takes 2 or more reactants and combines them into a product. So this is going to be a synthesis reaction. And this one isn't too bad. It's just going to be one single molecule. So it's going to be calcium bromide. Oh, what happened to my whiteboard? Oh, there it is. It hid from me for a second.
your laptop, your computer's jealous again, huh?
Yep. I think part of it is operator error, though, to be fair. Calcium bromide. And this is a I should spell it properly. That might not be a bad idea. Synthesis reaction. Oh, it's especially bad during mathnasium when I teach mathnasium online. Sometimes I even have to threaten to throw it out the window and then it starts working again.
Yeah, it starts talking after all this time.
Yep. We've got ways to make you talk. And the kids think it's the funniest thing ever. I say to my computer, straighten up and fly right, or you're going to be flying out the window, and they just crack up for the next 10 minutes, and they don't focus, they don't do any work. So I've learned not to do that.
Why do they laugh?
I don't know. I don't know if they're laughing at my pain or if they think that just the situation is funny. I'm not sure. Maybe just the mental picture of me kicking my computer out an open window is funny to them. Who knows?
Probably.
Kids these days, who knows what they think.
Kids are insane. Yep, I got it.
Alrighty. Up next, we have methanol reacting with oxygen. So methanol is going to be CH3OH, and methanol just occurs naturally in a liquid form at standard temperature and pressure, STP. And then we have oxygen always appears in diatomic form. So that's why we have to have the two there. So this, let me label it. So this methanol is liquid. And then, of course, this oxygen we know is a gas. So we need to decide what kind of a reaction we think this might be. Any suggestions? I'll give you a hint. Look at the second product, or look at the second reactant.
Oh, it's combustion.
It is combustion, yes. Every time we have something reacting with O2, it's going to have to be a combustion reaction. So let's see if we can predict the reactants, or the products. I don't know why I keep getting them switched. Let's see if we can predict the products. So do you remember what the products always have to be in a combustion reaction?
No.
It's always going to be carbon dioxide and water in combustion. All right. Next up, we have pure copper reacting with, yikes. This is I don't remember this one. I'm going to write down the chemical name first. So this is copper reacting with Pb. I know that's lead. And then we have manganese on the inside reacting with oxygen. So I'm going to put the subscripts in. So this is going to be O4, 2. And then I don't remember what this one is, the compound name for this. I'm going to look it up. Oh, this is lead-2 permanganate.
Permanganese?
Permanganate. Try saying that 3 times fast.
Permanganate. It's a bit redundant.
Redundant or not, I probably can't do it. Sometimes I have trouble with seashells by the seashore. And this is on another level. Permanganate. Lead-2 permanganate. What kind of a reaction do we have?
What type of what?
What type of a chemical reaction is this?
It is
So we have a metal, and then we have another compound featuring a metal and then a non-metal. So what do you think would happen when these two come together? We know it's not a combustion because we don't have something reacting with O2. We know it's not decomposition because we have more than one reacting. So that narrows our choices quite a bit. We have single replacement and double replacement and synthesis. Of those 3, what do you think it could possibly be?
I think it could. I'm not too sure.
So if this reactant right here if this were a gas, then that would probably be a synthesis. But because we have copper in a solid form reacting with this lead-2 permanganate in aqueous form, that's going to have to be a single replacement. The metals are always going to switch places. So lead metal is going to switch places with the copper metal. So this is a single replacement reaction. So let's see if we can predict the products. Here, I want to see if you can do that. See if you can predict what the products might be, considering that this is a single replacement.
So it's going to look like C plus PB equals.
So what happens in a single replacement reaction?
In a single replacement reaction, what happens is that it's going to be Cu MnO 4,2 plus Pb.
So instead of the copper appearing alone, we're going to have the lead appearing alone now. And we're going to have lead plus, and we're not going to have lead-2 permanganate. Now we're going to have copper-2 permanganate.
Yeah.
Permanganate. Next up, we have iron reacting with sulfur to produce. I want to see if you can figure this one out. So let's label everything first, and then let's see if we can predict the reaction type. So this is solid iron reacting with solid sulfur. We're trying to figure out what kind of a reaction this might be. Any guesses? Well, what could it not be? Which reaction types can we rule out right now?
We could rule out decom. We can rule out that.
Yeah, it can't be a decomp. You're right. Could it possibly be combustion?
Perhaps.
So what has to happen in order for it to be combustion? There's one very special reactant we have to have in order for it to be a combustion. Do you remember what that is?
It has to only have one reactant.
You're thinking decomposition. So to have decomposition, it only has to be one thing being broken up into multiple products. So what happens when you burn something? Let's say you throw something in the fire. What happens? What kind of a chemical change is happening when something burns?
When something burns, well, it's a physical change.
Well, oxygen heats up. Oxygen gets so hot that it starts bonding with things that it normally wouldn't bond with. It completely alters the chemical molecular makeup of whatever it is bonding with, and then it produces carbon dioxide and water. So for it to be a combustion, we always have to have O2. Without a source of oxygen, we can't burn anything. We can't have a combustion reaction without O2. So this isn't decomposition. It's not combustion either. We can tell it's not double replacement. We know it's not single replacement either because we have just one single element in both of these. So that means it can't be any kind of a replacement. So that leaves just one choice for the reaction type. What would that be?
That would be single.
So I'm sorry, could you repeat that?
It's not.
It sounded like you said it. It sounded like you said something very close to it. This is a synthesis reaction.
Yes.
All right. Next up, we have cadmium. CD is cadmium, and then we have CO3. So CO3 is always going to be carbonate. So this is a cadmium carbonate. And then we have any other reactants? Nope, this is the only reactant. So let's go ahead and label. Actually, there's only one thing to label. What kind of a reaction do you think this one is, based on the fact that we have just one single reactant?
It will be decomp.
Absolutely. So it is going to break up into. So we know the cadmium is going to be alone. So in a decomposition reaction, typically, if there is an opportunity to form carbon dioxide, that's definitely going to happen. So is it possible to extract at least one molecule of carbon dioxide from this, keeping in mind that carbon dioxide is CO2? Is it possible to get CO2 from this thing?
Is it possible to get CO2 from that? Yes.
Absolutely. We have the C. We have 3 O's. We only need 2 O's, so we can absolutely form carbon dioxide from this. And like I said, whenever there's an opportunity for that to happen, it will always happen. So we're going to have carbon dioxide with something else. What do you think the other product would be if we know one of them is carbon dioxide?
It will be.
So if we take carbon dioxide, what's going to be left from our reactant? If we eliminate a carbon and we eliminate 2 of our oxygens, what do we have left over?
CO2.
Well, we don't have C anymore. So if we look at this on the left side, if we look at our reactant, if we eliminate the C altogether, if we take out a carbon, we take out 2 oxygens to make carbon dioxide. What we have left is cadmium and one single oxygen. So that's going to have to be our remaining product. It's going to be CD.
CO.
So, yep, so that's cadmium oxide.
Ah.
Next, we have magnesium. We have MgS. That is magnesium sulfide. We're reacting with bromine. So magnesium sulfide is just going to have that 1-to-1 ratio, but then bromine always appears diatomically like that for the same reason why oxygen always does. So what kind of a reaction do you think this one might be based on the reactants?
Perhaps it would be synthesis.
It's a good guess, but this one doesn't seem to be synthesis.
Is it single?
This is single, yeah, single replacement. The clue is in what kind of reactants we have in the form. So this is going to be synthesis reaction. Synthesis reaction. Whoa. So what would be the product or products?
There would be MgSBr2.
Well, in this, oh, hang on a second. I said one thing and typed the other thing. It's not synthesis, this is single replacement. Sorry. I just typed the wrong thing for some reason. It is single replacement. So whenever we have a situation like this, we know that we're going to have either the S is going to switch with the bromine or the Mg is going to switch with the bromine. So what's going to happen is the sulfur is going to switch with the bromine. So instead of having magnesium sulfide, we're going to have magnesium bromide. And pure sulfur. All right. We have just one single reactant. What does that make you think of?
Decomposition.
Perfect. So let's see if we can name this thing. What does K represent? What element is that?
K, I believe that. No, that's not sodium, right? It's iron.
It's one of those that does not match the first letter of the thing it represents. A lot of them are like that. Like silver is Ag, gold is Au. K is just like that. K does not. K does not represent the first letter of the thing it stands for. K is actually just potassium.
Ah. Oh.
And then what about, do you know what OH is? So OH is a really common compound on its own.
No, what is it?
So we know H is hydrogen, O is oxygen. So together they make hydroxide. It's kind of like the combination of hydrogen and oxygen. So hydroxide is what we get. Potassium hydroxide. And I said it is decomposition, which is absolutely right. So we have metal reacting with a gas. And in a decomposition reaction like that, the metal is going to separate itself. It's going to disintegrate itself from the gas. So we're going to have potassium out on its own. And then we're going to have the hydroxide molecule on its own as well. And like you said, this is decomposition.
Yep, let's continue. This is next on combustion.
Let's take a look. So we have magnesium reacting with a water molecule, H2O. So how do we know if something is or is not combustion?
It doesn't have an O2.
There has to be an O2, exactly. And it has to appear by itself. So for example, we have water. What if we had another oxygen bonded to this water? It still wouldn't be combustion because we have to have O2 in its pure form without anything else for it to be combustion. So the hydrogen being there means it can't possibly be a combustion reaction. So our first reactant is just one single element. Our second reactant has two. So what do you think this one might be? What kind of a reaction?
It would be maybe a double reaction.
Well, a double replacement would occur if we have a 2x2, where this would switch places with this, and this would switch places with that. As it stands, we have a 1x2. So the magnesium is going to switch with either this molecule, or sorry, I keep saying molecules when I mean atom. The Mg is either going to switch with the H2 or with the O. So it's going to have to be a single replacement because only one switch is occurring in this one. So what do you think the products would be now that we know it's a single replacement?
They would be, let's see, they would be Mg, or, maybe just MgOH2.
Excellent. Very nice. So we have, this would be, I think it's just magnesium oxide. Yeah. Let me just verify that real quick. Yep, magnesium oxide. And we have dihydrogen, but if you wanted to write hydrogen, that would be fine because it's just like oxygen. It never occurs by itself. It always occurs diatomically in nature. All right, we have C2H6 reacting with O2. I think this is ethane. Let me just verify that. Yep, ethane. So we have ethane reacting with oxygen. We want to see if we can tell what kind of a reaction this is. So what kind of reaction do you think this is?
This is combustion.
Mm-hmm. It is indeed. So what happens in a combustion reaction? What are the products always going to be?
They are always going to be those.
The combustion reaction is always going to result in carbon dioxide and water. All right, now we are moving on to the next part, next page. So all the reactions are either single replacement or decomposition. And then there are different subtypes for each of those. So we wanted to take a look at what kind of reaction this is and describe the reaction as specifically as possible. So we have, this is magnesium, and then CO3 is carbonate. So this has to be a magnesium carbonate. And then it's just one single reactant. So what kind of a reaction is it going to be?
Perhaps decomp.
Sorry?
Decomp, maybe.
This is decomposition. So let's write down all the reaction types that are acceptable for this section. So we have single replacement metal, single replacement non-metal, and then we also have decomposition, chlorate, decomposition carbonate, decomposition hydroxide, and then we have just a general decomposition. So of the 4 decomposition reaction types, which one do you think this would be?
Of the 4, carbonate.
This one, well, let's take a look at what we have. So we have magnesium, Mg is magnesium, and then we have chlorate. So magnesium chlorate, this is going to have to be a chlorate decomposition because we have chlorate appearing in the product. So this is going to be a chlorate decomposition. And then this one, they don't really want us to predict the reactants. They just want us to identify the reaction and then we're done.
Easy enough.
And as always, let me know when you're ready to continue.
Yep, I am.
All right. So next we have just one single reactant. We know it's going to be decomposition, but we want to determine what kind. So we know Fe is iron. OH, do you remember what the OH2, or just what OH represents? What kind of a compound is that? It's an oxygen and a hydroxide. No, I kind of gave away the answer. It's an oxygen and a hydrogen, so they form a hydroxide. So this is iron, 2 hydroxide. So we have just one single reactant, so we know it's going to be decomposition because there's just one. But what kind of decomposition are we looking at here? And I'm going to write the next one while you're thinking about that. So which one do you think this one might be?
Number 4?
Oh, number 2.
Number 2. I think it might decomp hydroxide.
Yep, exactly right. Decomposition. Number 2 is decomposition hydroxide. Perfect. And then we have number 3. Just one single product, and that is water. So what kind of a reaction do we have here?
We have a for number 3, we have H2O, meaning hydroxide again.
Well, this is water. Remember, for it to be hydroxide, we have to have an oxygen bonding exclusively with hydrogen. So we would have to have something like this, and then some kind of a subscript to tell us the quantity of the ion, but we don't have that. We don't have a chlorate, a carbonate, or a hydroxide. So this is actually just going to be a general decomp for number 3. Let me know when you're ready to go on.
I am.
Next, we have number 4. We have lead reacting with MgCl2. So PB, that is lead. But what do you think the chemical name for the other reactant could be? Let's see if you can name that for us. What is Mg? What element would that correspond to?
It would be Mg.
Mm-hmm.
That would be
Magnesium.
Yeah.
Mg is magnesium. And then Cl by itself is chlorine, but when we have chlorine bonded with something else, the chlorine turns into a chloride. So this is magnesium chloride. So we know that it's not decomposition. It's either going to be a metal or a non-metal single replacement. How do we know which of those two it's going to be?
We will know by
we know things are going to be switching. We have a lead. Lead is a metal. Magnesium is also a metal. So we have metal switching with metal, which means this is going to be a metal single replacement reaction. All right, and as always, let me know when you are ready to continue.
Yeah. Let's go.
Okie dokie. We have just one single reactant, so we know it's going to be decomposition, but we want to figure out what kind it is. And we want to name this thing, because when we have a name for it, it'll give us a really good idea of what kind of a reaction it has to be, what kind of a decomposition. So let's start with the Zn. What does Zn represent? Which element is that?
Zn, zinc.
Perfect. Now, what about OH?
OH?
We know
that
oxygen and then H is hydrogen. So what is it called when they kind of come together to form one thing? It sounds like one word made up of different parts of oxygen and different parts of hydrogen. Do you remember what that is? Starts with an H.
Hydrogen.
It starts with hydro, and then there's something else after that. Hydroxide. This is
hydroxide. Yeah.
hydroxide, yes. We have zinc hydroxide. So what kind of a reaction do you think this one would be?
It is going to be perhaps it's going to be metal.
Well, we only have one reactant, which means that it can't be single replacement. It has to be a decomposition reaction. But what kind of decomposition are we looking at? Well, look at the name of the thing we have, and that'll give you a pretty big clue about what kind of a decomposition we have. So because we have... Sorry, what was that?
Yeah.
Go on.
Zinc hydroxide.
Exactly.
Maybe decomhydroxide.
Yes. Exactly right.
Yeah, let's continue.
All right. Number 6, we have CD. So CD is cadmium, and then we have it bonding with some other compound. So it's always a really, really good idea to name it first before doing anything else, because if we can name it, it'll give us a lot of clues about what kind of reaction we're dealing with here. So CD is cadmium. But then we want to see what the other stuff adds to that name. So whenever we have a subscript outside of a compound like this in parentheses, we have a compound in parentheses and then a subscript outside. That means we're going to have this followed by the number, followed by whatever this is. So this is going to be cadmium 2 something. And the way we use the Roman numeral analysis notation for that. So it's going to be cadmium 2 something else. So now we want to find out what the something else is going to be. Cadmium 2 what? Sometimes it's too easy to understand. Sometimes it's easy, sometimes it's not so easy. So let's take a look at what we have in parentheses. So we have Cl is chlorine. O3 is, we know that's just going to be some form of oxygen. So if this were ClO2, a 2 would end with it. I can't talk today. A 2 would end in "ide." Whenever we have a 3, it ends in 8. So this right here, this is chloride, but this right here is chlorate. So whenever it ends in a 3, it has the 8 suffix. Whenever it ends in a 2, it has that ite suffix, ide suffix. So this is cadmium 2 chlorate because the thing in parentheses ends with a 3. It's hard to remember this stuff. I remember when I took chem, I had to make note cards and I had to review them over and over until I just remembered this stuff after a while. So this is cadmium 2, 3. We have a 3, so that is chlorate. And now we just have to determine what kind of a reaction this is. Let me know if you have any ideas.
Chloride.
Yep, absolutely. Decomposition chlorate.
Let's move on.
All righty. We have number 7, table salt, otherwise known as sodium chloride. What kind of a reaction do we have here?
We will have a...
Is it going to be single replacement or is it going to be a decomposition?
Maybe a single, maybe?
Well, for it to be a single, remember we're going to have at least two different reactants because we know there's going to be some switching involved. Because we only have one single reactant, it's going to have to be decomposition. But what kind is that going to be?
What kind?
Yeah, what kind of decomposition?
It will be a carbonate.
This would be actually general, because if we look at the compound name, we have sodium chloride. So in the list we have for decomposition, we have chlorate, carbonate, hydroxide, and general. So because chloride doesn't appear anywhere in the list, I mean, we have chlorate, which sounds similar, but it's not similar enough. Because we don't have chloride, we're going to just go with general for this one.
Okay, let's continue.
All right. We have SN is tin, and then in parentheses we have CO3 and then a little subscript 2 on the outside. So it's just one single reactant, which means it has to be a decomposition. We want to determine which of these four it's going to be. So the key is to look at what we have in parentheses. The fact that this is tin doesn't really help us that much. This is going to be chlorate. So whenever we have CO3 in parentheses like this is automatically going to be chlorate. So this has to be decomposition chlorate.
Nice. That's Yeah, let's continue.
All righty. All right, we have just one reactant. What kind of a reaction is it? Is it going to be a single replacement or is it going to be decomposition?
It is going to be a single replacement.
So what has to happen for something to be a single replacement? What goes on in a single replacement reaction?
I plead the fifth.
So remember, in a single replacement reaction, things switch around. In a single replacement, we have to have at least two different reactants. And then we would have something switching with something else in the other reaction. Whenever we have only a single reactant, we can't have any kind of a single reactant. So whenever we have one reactant, it has to be a decomposition. So just to remember that every time we have only one single reactant, it has to be decomposition. It has to be one thing being broken up into two or more. So now we want to just determine which of the four decomposition types this one will be. So K is potassium. That information doesn't really help us name the reaction. This thing will. So do you remember the name of the OH compound? It starts with an H and ends in ide. Think you got it?
Yes, I have.
What is it?
Dihydroxide.
Hydroxide, yeah. OH is always hydroxide. So that we have a hydroxide decomposition.
Yeah, let's continue.
Right. See what we have. We have lithium, and we have something else. We have Mg, NO3 on the inside. So NO3 is always going to be a nitrate, and then we have a 2 on the outside. So we have two things, which means it cannot be a decomposition. It's going to have to be either a metal single replacement or a non-metal single replacement. What is Li in this compound, in this reaction? Li, remember?
Lithium.
Perfect. And what about Mg? Mag something.
Magnesium.
Excellent. Magnesium, and then in parentheses we have nitrate. So this is magnesium nitrate. So is lithium a metal or a non-metal?
Lithium is a metal.
Yep, exactly. Think about batteries. Batteries use lithium-ion technology, and that is a metal. Batteries definitely use metal. So that's just kind of how I remembered lithium was a metal when I took chem all those years ago. What about magnesium? Is
magnesium?
Sorry, is that a metal or a non-metal?
Non.
Magnesium is a metal, actually.
Oh.
Lithium is a metal. Magnesium is a metal too. So we're going to have a metal single replacement because we're going to have the metal switching places.
Oh. Single replacement metal.
Mm-hmm.
let's continue.
Alrighty. Next up, we have just one single reactant. So what does that have to be? What kind of a reaction is that going to be?
It is going to be it is going to be decomp general.
It will be decomp, but let's just verify if it's general. So let's take a look at what we have here. We know Na is sodium. We have sodium, and then what does CO3 mean? We know C is carbon, O is oxygen. So do you remember what CO3 makes up altogether? Do you remember the compound name for all of that appearing together?
Carbon trioxide.
Well, this is going to be carbonate. Whenever we have CO3, that's going to be carbonate. So whenever we have CO2 would be carbon dioxide. CO3 is going to be it's going to be carbonate. So whenever we have a 2 subscript, it's an "ide" ending, and then whenever we have a 3 subscript, it's an 8 ending. So this is going to be sodium carbonate. And we do have carbonate in our list of decomposition. So this is going to be a carbonate decomposition reaction.
Yep, I got it.
All right. We have iron reacting with sodium, bromine. Do we have any guesses about what kind of a reaction this might be?
It will be perhaps. I want to say decomp general.
Well, this is going to be a single replacement because we have one thing that's going to be switching places. So the iron is going to either be switching places with the sodium or with the bromine. So is iron a metal or a non-metal?
Iron is a metal.
All right. Is sodium a metal or a non-metal?
Sodium is a non-metal.
Sodium is actually a metal, and then bromine is a non-metal. So this is going to have to be a single replacement metal reaction. So the metal is going to switch with a metal. We're going to have sodium, and instead of sodium bromine, we're going to have iron bromine. Or actually, I think it's going to be ferric bromide would be the technical name for this. I think that it would change into ferric bromide, but the main thing to consider is that this is metal single replacement.
So it's going to be a single replacement metal.
Yep, single replacement metal.
So the next one will be decomp hydroxide.
Yeah, absolutely. What kind of tipped you off that it would be decomp hydroxide?
Probably VH.
Yep. OH is always going to be hydroxide. So good call. Very nice.
Yeah, let's move on.
Good idea. So we have number 14. This is calcium. And then do you remember what CO3 is?
CO3, carbonate.
Perfect.
Decom.
Calcium carbonate is what we have. So what kind of a reaction would this one turn into?
It will turn into decomp carbonate.
Excellent. Very nice.
Let's continue.
Aye, aye, Captain. So which of the subgroups is it going to be? Is it going to be single replacement or is it going to be decomposition?
It is going to be single.
Yep.
No, yeah.
You're right. It is single replacement. We have two reactants, so that's how we know it can't be a decomposition. So we have iodine reacting with potassium, and then Cl is going to be chloride. So of the four, or is it going to be a metal single replacement or a non-metal single replacement?
It is going to.
Iodine is, I'm pretty sure iodine is a metal. Let me verify that real quick.
Yeah, I'm pretty sure as well.
Well, iodine is non-metal.
Oh.
So the iodine is going to switch with something. And because iodine itself is not a metal, this is going to be a non-metal single replacement.
Let's move on.
All right, our last problem of the evening. I know you're probably upset we don't get to do more, but I'm sorry to hear that.
Sad world we live in.
All right. 16. What we have is Sr, that's strontium, and then we have a hydroxide compound bonding with that. So we have, I think this is just strontium hydroxide. OH2. Yep, strontium hydroxide. So see if you can figure out what kind of reaction this one would have to be.
Perhaps decomp hydroxide.
Yep, absolutely. So this is our last problem from the problem set. Is there anything else you want to go over at all tonight, or are you ready to just be done with chem for the weekend?
Yeah, let's do a quiz I have right this second.
There's a
sarcasm. No,
Oh.
I'm too tired right now.
It's all right.
Could we work on the quiz tomorrow?
Oh yeah, sure. Is it going to be on this material?
Yes, I believe so. Let me double check though.
All right, tomorrow is Saturday. What time is good for tomorrow? I mean, I'm open pretty much from 6 a.m. until about 3 p.m. What time is good for tomorrow?
Is 3 o'clock good?
Could we do 2?
Yeah, sure.
All right, sounds good. Well, you are free to go whenever you're ready. Have a wonderful evening, and I'll see you tomorrow for some more chemistry fun.
See you then. Bye.
Adios.